would basically be what the first unit of electromagnetics, the physics the electromagnetics test would be. It's all about electric charge, field, and force. It's basically the basics on this. So obviously electrostatics talks about electricity and electrically charged matter, and we can just talk about what charge is, how do things get charged, how does charge behave, and Coulomb's law. I think this presentation will definitely be longer than an hour, so we'll just see how far we can get into this by set. Okay, so what is charge and where does it come from? And how can net charge be created? Objects can be basically charged by rubbing two different surfaces together. Charge is basically if there is a discrepancy in the number of electrons something possesses. Obviously, you've probably seen like the structure of an atom before. It's in the center, there's a nucleus that's made up of like protons and neutrons. And then outside here is basically an electron cloud. It's a cloud of like many different electrons. All these electrons have minus charges, and if you rub something on that has like a relatively positive charge, the electrons will start to try to cling onto the positive charge because positives and negatives attract. So this would start taking away electrons from this system, and then this system, since it has a shortage of electrons, it has a positive charge. Now, why is it called positive and negative? Just due to convention. Actually really comes from Ben Franklin, who, after discovering that things can be electrically charged in 1793, he just decided to just name one thing. If you rub silk and glass, you can actually you can get like a static charge. He just decided, oh, the thing, like one of these two materials is going to be the positive charge and the other one's going to be the negative charge. It was random, and now we have what positive and negative are. And this thing opened. Okay, so obviously electricity really comes from the atomic level. Obviously, the parts of the atom are a nucleus that's comprised of protons and neutrons. So it has a relatively positive charge. And like I said before, there's an electron cloud. It's basically almost all of the space that an atom is. And it has the opposite charge of a nucleus, and the charges are equal because the atom overall has a neutral charge. Now, what's the relative volume and mass of a nucleus and electron cloud? They're both tiny. For example, the mass of one electron, if I remember correctly, is like 9.11 times 10 to the power of -1 kilograms. It's an absolutely like mind-bogglingly like tiny number. Yeah. Convention, like the most popular diagram for showing this would be the one on the left, but this is not really realistic. A more realistic representation is this right one, where the nucleus is just a tiny speck in the center of the atom, and it's just surrounded by electrons and charge. So, obviously, you should probably know this, but charge is in two opposite types. There's two different types of charge. You have positive and negative charge. So this is just actually like the positive and negative poles you would see on a magnet, but we're not going to go there since that is pretty advanced stuff. Okay, so charge should be conserved. Whenever you're transferring charge, you should not have a surplus or a shortage of like one type of charge over another. If your system is closed and your charges are not leaving, like for example, into the ground or something, your net charge should be a constant number, and the arithmetic sum of the total charge cannot change. Electric charges are basically significant because they can create forces. Just like how gravitational force is like two masses that are attracting each other, electric forces are two charges that are either attracting or repelling each other based on the relationship between the charges. These forces affect the masses that contain the charges, and then they can be analyzed using standard mechanics. Unlike with gravitational force, they can be both attractive and repulsive. Gravitational can only be attractive because everything has mass. Net electric charges of same sign repel each other. Electric charges of different signs, they attract each other. You probably knew that already, though. So yeah. Now, this kind of goes into the next thing we're going to talk about, which is basically charging by conduction and induction. So, conductive charging means that you are charging by directly pressing a conductive material against another. This facilitates the transfer of electrons between two objects directly. I feel like that's kind of like straightforward enough, but if not, here's kind of like an example, and it's this one on the left. So let's say we have something neutral, but it can conduct electricity. If you put a charged metal object, as obviously all metals are conductors, if you put a charged metal object next to and in contact with this neutral metal charge, the electrons will actually pass through this area where they are touching each other, and they will travel to up to this positively charged thing in order to help balance out the difference in charge. So then once you pull these away, this will have a more neutral charge, and then this previously neutral metal rod will have a relatively positive charge near the area where the two objects were in contact. An inductive way of charging is basically the same as conduction. The same thing as conduction, but the objects don't actually touch, and it's mainly the shifting of electrons is just due to attraction and repulsion. So let's look at this diagram on the right. So you have this object A that's neutral and connected to the ground. This means that this is connected to the ground, which is neutral. The only things that can pass through this wire would be electrons, and when the electrons go into the ground, they dissipate. So this kind of like is this canceller of charge. So let's say you bring a negatively charged object near this positively charged object again. So you would have a positive charge near the part of the rod that is closest to the negatively charged item. This is because this negatively charged thing, since protons, the nucleus of an atom, cannot move, but electrons can be passed between atoms, the electrons here will start moving towards the other end of the rod, just due to being repulsed by this object. And then the electrons will travel through this wire and dissipate. So once you disconnect this from the ground, your object will have a net positive charge. Okay. Electric insulators and conductors. You probably know what these are already since you've taken middle school science, I assume. But in case you don't know, an insulator is basically something that does not allow electricity to flow. That means that the electrons cannot flow throughout the surface. The conductor is a material that allows electric charges to flow freely. Examples of both include metals, ionized liquids, certain types of chemical compounds such as potassium and sodium chloride. So, those are like examples of solutions. Carbon, and obviously you probably know water is also a pretty well-known conductor. Insulators, otherwise sometimes known as dielectrics, are things that prevent flow, and examples include organic solids such as like wood and stuff, um, polymers, traditional ceramics, non-ionized fluids. That means fluids where you didn't induce a charge in, or fluids that basically that are not made of ionic bonds, um, and certain types of gases. And then obviously you have most of the materials, which are like the in-betweenish things. They are called semiconductors. And then a well-known example is silicon. Quantifying electric charge. So electric charge, just like mass, is a property, and it can basically be measured quantitatively. So the variable is Q. It can be written as either lowercase or uppercase. Did this screen sharing stop? Oh, okay. Okay. Anyway, so let's get back to it. Variables can be Q or Q. It doesn't really matter whether it's uppercase or lowercase, but although this uppercase Q is more commonly, it more commonly denotes like a Q if you want to put it in an equation, and this is the variable that you use when you're trying to like write Q in a term. Although the actual measurement, like the unit, is a Coulomb, which is named after a French scientist. A Coulomb is a massive amount of charge. Rather large is pretty much an understatement, as we might see later on. So normally we don't use coulombs to measure charge. We normally use microcoulombs. If you didn't know, micro is the metric prefix for 1/1,000,000th. Then you also have nanocoulombs, which is a billionth of a coulomb. However, the smallest possible charge is E, which is basically the charge of an electron or proton, since they're equal. All other charges are some multiple of this, and E is approximately 1.602 times 10 to the power of -19. You don't normally have to remember this number. It will appear on most formula sheets in physics, but it will still be good to be familiar with this number, since a lot of electrostatics does actually talk about how do electrons move. So knowing the charge of an electron is pretty helpful, and you have to consult formula sheets for it. Okay. We have found experimentally that the electric force between 2 point charges is proportional to the product of the charges, and inversely proportional to the square of the distance. Wait, no, not the square, the distance, inversely proportional to the distance. This is basically the same thing as the law of universal gravitation, except obviously you switch out the properties so that it describes electric force instead of gravitational force. Normally, you don't, again, normally due to this, since the distance between electrons are just tiny, you really don't need much charge to create like visible amounts of force. It really takes like a few nanocoulombs to create several newtons of force. And small masses, as in gravity, require a huge celestial body to produce similar gravitational forces, just because of like that perspective of distance. So this is your formula. Your electric force is equal to -k times Q1 times Q2 over R squared. So K is a constant. This is one of your fundamental constants, and that is called the Coulomb's constant. This is basically 9 times 10 to the power of 9 Newton meters squared per Coulomb squared. It's like the same thing as like your universal gravitational constant, except it's for electricity instead of force. And then Q1 and Q2 are the charges of the two items you're trying to calculate the force between. R is the distance between these two, and it's squared. Okay. The reason it's negative here is because if these two, for example, if they are positive, if Q1 times Q2 becomes positive, the force between the two would be repulsion. So you need to put your negative here because you're trying to measure the amount of attraction between them. If they are, if the force is of repulsion, it has to be negative. But if these charges are the same, the product will be positive. So just balance it out with the sign. This is unlike, again, the law of universal gravitation, where you will not see a negative sign there. So yeah, just to make note of that. On the bottom, you have the law of universal gravitation, where G is an absolute. So the R squares or the mass have to be huge numbers for there to be a substantial amount of force, and as well, this can only be positive. So you can see the fact on the bottom, but if you can't like share like the share screen cropping it out, it says that the gravitational interaction between two objects is about 10 to the power of 34 times weaker in the universe compared to the electric interaction between two objects, if whether they have the same mass or same charge. Okay. Again, the direction of the electric force is basically along the line connecting the charges. Since force is in fact a vector, you have to typically know the direction. So you can see like examples on the diagram to the left where these are the distance between these two, the path between these two particles are all horizontal lines, so the forces must be horizontal. And then we also know that these force vectors tend to be equal for the most part because of Newton's third law. That law cannot be broken by any circumstances. Forces will create an equal and opposite force. So those vectors all have the same magnitude. Okay. Okay. So just to let you know how big of a charge a Coulomb is, let's say if two objects, no matter how tiny they are, like they could literally be grains of sand, or they could be like a normal ball for visualization. If two objects each had a charge of +1 coulombs and were positioned 1 meter apart, what electric force would they exert on one another? Since we know Coulomb's law, you can just plug in the numbers. So you would have Fe equals -9 times 10 to the power of 9 times 1 over 1 squared, which is -9 billion newtons. Which means that if you have two objects with a coulomb of charge each, you position them about 3 feet away from each other, and then you like let like the electric force do its thing, they will speed away from one another really, really fast. Like, jeez. If you want a comparison, if you have a space shuttle that's loaded to full capacity, again, that would be a launch force of about 40 million newtons to get it out of the atmosphere. This K, like we talked about before, we know it's 9 times 10 to the power of 9, but K in reality is actually 1/4 times E naught or epsilon naught in this scenario. So E naught is basically the permittivity of free space or vacuum permittivity. It basically measures how well can like an electron penetrate like the vacuum of space. So how well does electric field go through a vacuum that is like space? Um, this number is 1 over 4 pi k, and then k is 1 over 4 pi epsilon naught, and that number is about 8.85 times 10 to the power of negative 12 Coulomb squared per Newton. If you're taking college board physics C, this is the formula you get. If you're trying to look for Coulomb's law, they don't write K, they write 1 over 4 pi epsilon naught. Like the speed of light, which is denoted as c and pi and g, epsilon naught is one of the most fundamental constants of universal physics. Sometimes some annoying questions in physics will ask you about instruments that they use in the lab. And one of the instruments that they use in electrostatics is something called the electroscope, which is used to detect what kind of charge it is, what kind of charge some object has, since that's not normally visible. So an electroscope has a few components. There's an insulator that holds a rod, and on top you have a wire going through this. You have a metal-like detection, a detector, and on the bottom you have 2 gold leaves. Now gold obviously is a metal and it is a conductor. So basically what this electroscope does is that it shows you you basically look at how these gold leaves behave when you put something close to it via conductive or inductive charging, and the behavior of these should tell you what kind of charge this has. So for example, if you have a positive charged item, you would basically have a lot of like the negatively charged items, the electrons, move up this wire and to the metal ball because opposites attract. So this will leave these two leaves with mostly positive ions, and then they would end up repelling one another. And now, if you do it this way, if they don't stretch as far compared to like this, or if they don't like move as quickly, that means that the thing is just weaker. The charge is weaker. It doesn't pull that many electrons away, so you can also kind of tell that from this instrument. Now, another way of doing it is you charge the electroscope metal by itself. So let's say we do it with a negative charge without losing generality. So let's say we put a negatively charged item here. So the electrons will be repulsed by this and they'll move down. And then this part would be full of like it would be densely packed with negative ions, and they will move farther apart from one another compared to like the default position. If you put a positive thing here, then the electrons on the bottom will get attracted to the top, and excuse me, and these since the charge between the negative charge and repulsion between the 2 gold leaves isn't as strong, these 2 leaves will end up getting closer together. Now, Coulomb's law is for point charge problems. So basically, it's if you're given certain charges and you are trying to find the forces in between these objects. Now, note that you can actually, if you have multiple point charges, the net force is basically the forces on each charge from every other charge. You calculate those, then you add those up as vectors. So let's say we are trying to analyze the electric force for Q3. So we see that since Q3 is positive and Q2 is positive, there is a strong repelling force that's enacted on Q3 from Q2. And since Q1 is a negative charge, there'd be a weaker attracting force between Q3 and Q1 because they're further apart. So you can draw those two vectors and you can sum these up to create a net force vector for Q3 that you can see on the bottom. It's denoted as F without any of the numerals. So for example, let's find the net force on Q1. So this is basically one of the most basic problems there is you're just given charges on a line and you're just trying to like find what the force is between them. So this question is what's the net force on Q1? And basically it's asking you whether or not we should add or subtract individual forces. So how you do this is I'll not go through like the full solution, but I'll just give like a conceptual idea. So how I do this is just that for Q1, you just look at the other forces applied to it. So there'll be a big repulsion force by Q2, and there will be a small retracting force by Q3. So for Q2, you just use Coulomb's law. You should get a negative force that depicts the repulsion. And this force should be way stronger than Q3 because not only is the magnitude of the charge stronger, the distance is also smaller. So you would have a smaller force here. So you would just use Coulomb's law since we know both charges and the distances, and we'll just find the force that's left and the force that's right. You add those up, you should have a net force to the left, and you can do similar stuff for Q2 and Q3. Example in AP Physics, would be this kind of problem where you have a bunch of things on a triangle, and you are trying to find the electric force between those. So here, we know what the net force on Q3 is, and our job is to try to figure out what does this mean for Q2 and Q1. So determine the signs on the charges Q1 and Q2 and determine the correct signs below, whether they are negative or positive. So how you do this is that you look at Q3 and then you start writing, you start like saying how could you get that kind of result from adding vectors from sides that are like the same as that of the triangle. So we can do things like that. We know Q3 is a positive charge, and this is the general kind of force you need to get like the net force to turn left. So there should be like a force that goes down that's attracting to one of the two, and then there should be a repulsive force for Q1, exactly like how this triangle, this blue triangle looks. So since there's an attractive force between Q1 and Q3, we know Q1 is the opposite charge. So Q1 has to be negative. Then since there's a repulsive force between Q2 and Q3, Q2 has to be a positive charge. So now, the reason why we have to do it in this form, not with the other part of the triangle, is that the net force is directing left. If you try it with like the right part of the triangle, let's say this was going this way, and then the only possible way for this direction force to go is down here, because if it went up here, there'd be a part of the net force that's going up. It's not, it's horizontal. But if you add these two forces together, you have a rightwards force, so it doesn't work. So we'll just skip through this for now. This is the part of the electrostatics part that does kind of require calculus. And it's basically, let's say you have a charged bar and you have a uniformly distributed charge on the bar. Now let's say you have another point charge away from it. That's a charge of -5 microcoulombs. The bar is 30 microcoulombs and is 0.25 meters long. Now, what is the net force on the second object if it's 0.25 meters away from one of the tips of the bar? So the first thing you have to do is, again, plot it in a coordinate system. Make sure that you can easily reference the points. Don't make it complicated for yourself. So let's just set one of the tips at the origin and the other one at 0.250. So then due to this, one of the point charges would be at 0.50. Now, just like moment of inertia, you have to do this using calculus because it's a bar and there's distance involved. So you have to add the df components. This one is a circle, but it works the same for the line. You have to imagine that you split this line into infinitesimally small point charges that are all this 0.25, no, sorry, 30 microcoulomb long charge. Then you integrate that to get your total charge for the bar, and then you can do things like that. This is the same thing, but instead of a bar, it's a arc on the circle. So instead of here, instead of like doing things horizontally, you do things along a polar coordinate system since it's the circle, and it's easier to just work with that. So here you have an R of 0.4, and you have to add all of the df, all of the forces components. So you can imagine this like so. Like imagine each one of these again is an infinitesimally small point charge. This point x, it doesn't have to even be here. Let's say it's here. There's a force of attraction between these points. So and then here it also is the same. So here there's also a point. There's also attraction because this entire thing is just continuous. Then here too. So in time you just get like a bunch of different forces pulling in different directions. And in order to find this total, you have to integrate r with respect to d theta, the angle. So you can see this here. You would try to set up your thing as angular change density. So your Q would be some, let's say, call it lambda. This is your charge density and then times theta. So then your dq is lambda times d theta. And then if you're not doing this, if you're doing a line like you did last time, you would not use angular. Of course, you would use linear charge density, which is equal to Q over L, and you can differentiate with respect to that. So in this case, you can find the ds here. That's from your s being on the sides of this arc is equal to r d theta because it's dq. Then ds is equal to dl, which is dq over lambda. then so you could just multiply. So you can see it gets quite complicated, but as long as you're careful in what you write and can understand this comfortably, like in terms of conceptual, not in terms of math, I feel like if you are tested on this, you'll be fine. So far, do you guys have any questions? Okay, since I don't really see any questions, I'll just go on. Okay, so since each CF vector has a different direction, it cannot be added directly, and they must be split into XY components and integrated separately. So you can see this in the bottom procedure here. So you would have to specifically write in Fx as integrating all of the forces being pulled in the X component, and Fy, which is all the forces being pulled in the Y unit. Okay. So this doesn't work. Okay, so the next part we're gonna go to briefly is electric pulse. Make sure if you didn't really understand anything in section 1, you should really ask, since I get that it's hard to understand, but having a basic understanding is very important if you want to build a career around AP Physics, and especially E&M. Okay, so electric field is basically kind of like the same thing as your gravitational force, or sometimes potential energy, if you will, but they are not exactly the same. So let's start by going back to the analogy of gravitational force. So we know that the reason that Earth is exerting gravity on all of us is because the Earth is massive, and massive objects such as the Earth have strong pulls of gravity. So like basically, even if the object is there, you can still you can describe gravitational force as a force per unit mass. So for example, for universal gravitational potential energy, you have this formula Gm over r squared, and then if you plug that as like Fg mg, you would get G. So basically that kind of like even though it's not a specific force, it gives you an idea. This constant G gives you an idea as to how objects behave when subjected to gravitation. Even if you are not actually dropping an object, you still know that objects around Earth accelerate at a rate of 9.8 meters per second squared. Now, charge basically works the same way, but since rather than gravity influences due to charge, The electric field you just can't state an acceleration, expect people to know what you're talking about. You have to state that this is in fact an electric field line. Basically not acceleration, but instead how much force has been created over certain amounts of changes in in charges that is more important. So yeah. Our next question is, what is electric field? Again, we kind of went through that, but the electric field is the force that acts on a hypothetical small charge, basically an infinitely small, if you will, test charge on some electric field or some two objects undergoing basically undergoing some kind of like change, in charge and electric force between them. This small charge, if I didn't say this before, it's called a test charge. It's by default a proton, so you can definitely try an electron. E by formula is F over Q for point charges. So basically, it's your electric force divided by your charge, or force per unit charge. Its unit is not really different from what you would expect to be. It's a Newton per Coulomb. So the field vector v in respect to velocity does very much depend on how the people, or not people, how the charges have a relationship with each other in terms of that. So if they are positive, then they go in the same direction. If negative, they don't, yada yada. Make sure if you don't understand to unmute yourself and ask me. I'll be kind of like breezing over like a lot of this stuff. So okay, I don't really have much else to say, so we'll go on to the next one. So for point charge Q, the electric field on the charge is due to another charge Q on the distance r meters, actually we should go with, away, or equal to Fe over Q. Is some ratio being calculated by using E equals KQ over R squared, and E equals 1 pi E naught R squared. Oh my god, that's such a handful. Okay. Remember when you are solving a problem that is specifically asking you for electric field, draw a diagram. Show at all the charges. If a later part asks you to change or modify something in a graph or a diagram or whatnot, make sure you actually follow by these rules. It's important to not kind of like assume that just because it's electric field, you can just calculate it via point charges. Point charges only work for points. As the name suggests, if you're going down to linear applications, you actually need to integrate. So aside from strict superstition, some kind of like weird kind of like questions that might break expectations of how electric field should work, the AP Physics test has been very consistent in providing electric questions. I'm gonna skip this. This kind of gives you an idea of how hard it would be if you didn't have those kinds of formulas and you were trying to do it via a point charge, or in this case for a rod that has like a range of places where there's a charge, and the charge point, the test charge is not necessarily at the end. Next question is, find that, whatever. Field lines are basically lines that, just like how you can see lines when you're trying to draw a magnetic field, when you're trying to draw electric fields, you can also get lines. Um they always go from a high positive to high negative charge. Um Also, if you are drawing this in a diagram, the number or the density of these lines you pack next to a charge is an indicator of how strong it is. Basically, if it's a microcoulomb, there should be the line should be way more dense than a object with like about a nanocoulomb of charge. The electric field itself is stronger when the field lines appear closer together in small intervals. This shows that something called voltage, as we'll get into later on, is dropping deeply, and that's basically a good sign for growth in the electronics industry. A dipole is basically just two equal charges that are opposite of each other. Um, okay, there's not much else to say here again, so um, if you have two sign charges, it looks like that they're kind of like they're repelling each other. Um, you have to consider the E field from each charge in space. Remember, these two things cannot connect. And obviously, you can't look like an idiot on your college board by submitting pretentious imagery. That'll not get you any viewers. Okay, do you guys want to stop here, or should I continue? Hello?
Go on. Thank you.
Thank you. So if there's nothing else, I guess I'll see you guys later. Maybe if there's more time next week, we can go into this after we discuss AP Physics C a bit. Until then, I'm Jerry Liu, and this has been an AP Physics Club meeting. I hope to see you next time. So goodbye.